If you code in C or C++, chances are that you care about software efficiency. There are a lot of tips on the internet on how you could optimize your code, but some of these tips are not applicable and will not help your code run faster. Today we will be looking at how the compilers generate efficient assembly code and that these micro-optimizations at the source code level does not affect performance. Today we will be using Compiler Explorer to see how the assembly looks like under the hood. We will be using a 64-bit version of a GCC compiler and using the O1 optimization level. The compiler flag O0 would indicate no optimization, and using flags such as O2 and O3 will force the compiler to do more aggressive optimizations. On the left, we can write functions in source code, and on the right, we can see the assembly generated with the compilers and the given flags. Today, we will learn to read a little bit of assembly as well as some calling conventions. At the assembly level, we do not have variables. Instead, we work with fixed-sized registers to compute desired result. For functions that return integer values, the return value is stored in the RAX register. In this case, a C++ integer is 32 bits, so the EAX register is the lower 32 bits of the RAX register, and we can see the compiler directly moving the value 45 into the register before returning. We can already see that the GCC compiler is kind of jacked. It strips out the unnecessary for loop and gives us the answer of 1 plus 2 plus 3 all the way until plus 9. We are almost ready to explore some fake optimizations where modifying the source code does not generate faster assembly. But before that, let's first take a look at the assembly structure for a for loop. Let's replace the constant 10 to the parameter n. In assembly, the first integer parameter is stored in the RDI register. Here, EDI is just the lower 32 bits. Here we can see that the compiler chooses to represent the integer I with the EAX register, and using the EDX register to represent the result variable. The entire for loop is actually only 4 assembly instructions. First, we add I to the result, then we increment I. Then we compare I with the parameter n. Finally, we jumped to the L3 label if the compared values are not equal. JNE stands for jump not equal. If the compared values are equal, then we do not take the jump, and we fall through to the L1 label, continue to move the result variable into EAX, which is where the return value is stored. Now, what happens if we try and optimize this postfix increment with a prefix increment? Because some guy on the internet said that prefix operators are faster than postfix. Well, at the O1 optimization level, we can see that exactly nothing has changed. It is still the single instruction, add EAX by 1. It is worth mentioning here that the prefix and postfix operators may generate different amount of assemblies. But for a lot of common cases, such as in this example, postfix and prefix operator does not really make a difference. Next up, let's look at manual bit shifting. So here, instead of multiplying by 64, I explicitly shift the integer left by 6 bits, because shifting left by 6 bits is equivalent to multiplying by 64, and bit shifting operators should be faster than multiplication. In the assembly, we can see that the source code does map to a single shift arithmetic left instruction. However, if I replace the bit shifting with a regular integer multiplication, we can see that the assembly still hasn't changed. The compiler still recognizes 64 as 2 to the power of 6 and decides to use the SAL instruction anyway. In this case, at the source code level, we should write whatever code is more readable in the context, because the compilers are very well trained to replace power of 2 operations with bit shifts. Finally, let's take a look at the assembly structure of the ternary operator, because there's also a saying that the ternary operator is faster than if statements. According to System 5 calling conventions, integer arguments are passed in via RDI, RSI, and RDX registers respectively. Here, DL is the lowest 8 bits of the RDX register, which is the Boolean parameter passed in. The second instruction preemptively assigns the return value as EDI, which is the LHS parameter. Next, we have a conditional move, which conditionally assigns the return value as ESI, overriding the return value with the RHS parameter in the source code. So whether or not the cmove instruction actually overrides the return value depends on the most recent test on the Boolean parameter. So in this case, there are no jump instructions in the assembly. However, if we try to replace the ternary operator with a traditional if-else statement, we can see the compiler achieves the exact same. So in this case, it's actually still nice to just use the ternary operator because it's more concise. But under the hood, the compiler gives you the exact same assembly structure. So these are some common cases where the fake optimization on the source code does not really change the assembly structure in any way. When optimizing hot code paths, you should probably still look at the assembly and decide whether you are satisfied with it, or simply just profile it. In general, these compilers that we use today are based on optimization paths that has been developed for decades. So usually we could write some dumber source code and the compiler would still optimize the heck out of it.